All right, factoring. So, what is factoring? Write something as a product. That's what factoring is. Every number can be written as a product of other numbers in some fashion. Prime numbers. It's a positive number with only two factors, the number 1 and itself. Numbers that are not prime are called composite. That's what we're going to work with. The number 1 is neither a prime nor a composite. It's unique. Writing all the factors of a number. Okay, this is a skill that we need for factoring techniques. So we want to write all the factors of a number. And I think I have an example 14. I'll do this one with you. So usually what you did back in grade school when they taught you this technique, they usually did, there's 14, you draw a line, and then you start listing the factors. So you start giving me two numbers that multiply and equal 14. And you should always start with the number 1. So 1 times what is 14? 1 times 14 is 14. And then you just go down the number list. So after 1 comes 2, and you ask the question, does 2 go into 14? If the answer is yes, you put a 2 times whatever it is to get 14. And you just keep on going. Does 3, does 4, does 5, does 6, does 7, and 7 does, but we have 7 right here. So that means you have them all. So once you start coming up the other side, you know you have all the factors. So these are all the factors. These are the numbers that will divide evenly into 14. Okay? This is a skill we're going to be using for factoring polynomials and such, so we want to make sure we know how to do it. What is prime factorization? Prime factorization. Prime factorization is to write a number as a product of prime numbers. And since prime numbers are numbers that only have the factors 1 and itself, so these are kind of unique in that sense. And you can do this with any number. If the number is already prime that you're doing, then it's already prime, you're done. So let's look at 24. We'll use this example right here. Usually what I do in this case is do what's called a factoring tree. Factoring tree means I'm going to branch off two numbers, and you just got to find two numbers that multiply to equal 24. And it can be any two numbers you want. It doesn't matter. You can go however. There's a lot of different choices for two numbers that equal 24. But two factors that multiply and equal 24, I'm going to use the number 6 and the number 4. So once I've done that, I ask the question, is 6 a prime number? If the answer is yes, you circle it. That branch is done. If the answer is no, then it's composite. And so then there must be two numbers that multiply to equal 6. That is 2 and 3. Same question. Is 2 a prime number? If the answer is yes, you circle it. If it's not, you continue on, but it is prime. 3 is also prime. Now we still got to do this branch over here. So we go to branch for 4, and two numbers that multiply equal 4 are 2 and 2. And we've already established that those are indeed prime. All the circled numbers multiplied together is called the prime factorization. And we usually write it in exponent form. So this will be 2 to the third power times 3. So that is 24 as a prime factorization. And you can do that with all numbers. So those are some preliminary things we need to know how to do when we are getting ready to do factoring techniques. And here's the first technique that we need to know how to do. The greatest common factor, otherwise known as GCF. The greatest common factor is a technique. You can do it with the single numbers, and that means we're just looking for the biggest number. Like in this scenario up here, we find this is all the factors of 14, and actually we'll just do an example, and I'll show you what I mean. For numbers, let's do 24, and then we would do 16. So we're looking for the greatest common factor that would go into 24 and into 16. So greatest means the largest, common means it will be in both lists, and a factor means that it is numbers that will go into 24 and 16. So you just do this technique up here. 1 and 24, 2 and 12, 3 and 8, 4 and 6, and that's it. After that, we go back up the line. For 16, 1 and 16, 2 and 8, 4 and 4. So these are the factors of 24. These are the factors of 16. Common means it has to be in both lists, not counting 1. You never take 1. And the biggest one is in both lists. So as we go through this and look, we see that 8 is in both lists. So your greatest common factor for 24, and 16 is 8. That's how you would do with numbers. Using this technique. I'm now going to show you a different method. And this method also works. And it's actually a kind of the technique almost that you would use for all the polynomials that we're going to be dealing with. So this is kind of like where this one comes from. But for number portions, you can rely on this technique, was what you learned back in grade school, for finding the GCF for numbers. Okay? But if there's variables involved, we have to go one step more. And so that's what this next method is all about. So the next method kind of realizes and uses the prime factorization technique. Okay? So I'm going to show you the same example again. Anyway. So let's look at the 24 and the 16 again. So in this case, again, we do the 24, we break it apart. There's 6 and 4. This is 2, 3, and this is 2 and 2. We know this one is 2 to the third power times 3. We already did that one. For 16, we break it apart. We can do whatever you want, but I usually do 4 and 4, 2 and 2, 2 and 2. This is 2 to the fourth power. From this point of view, okay, we want to find the GCF, but it's in this prime factorization form. But remember, the GCF means the greatest common factor. It is the factor that is in both. So in this scenario, we can see that this one has a factor of 3, but this one does not. So that means 3 is not common. It's not in both of these numbers. So 3 is out. But the 2 is in both. The base number for 2 is in both. So I know that GCF is going to be what's called a power of 2. Well, what is that power going to be? Well, since it has to divide into both numbers, you need the one that's the smallest exponent. See that? This is a 2 to the third. This is a 2 to the fourth. 2 to the fourth cannot divide into this because there's only 3 2's here. There's not 4. But this one has 3 2's, right? 2 to the third means 2 times 2 times 2. And this one has 3 2's. It actually has 4, so it has 3. So the actual GCF is the smallest exponent on that, or 2 to the third power, which we know to be 8. So what I want to do for this is I want to basically look at both lists. If a base number is in both, if it's in both lists, then take the smallest exponent for that base. Then multiply for your GCF. And I'm going to show you another example here to kind of illustrate this with letters. So we don't have to do the different more numbers. Here's an example with letters and why this technique is what you want to use when we start dealing with polynomials or algebraic expressions, trying to find a GCF. So let's take, instead of 24 and 16, let's say one expression is 24x to the third y squared. And the other one is 16x squared y squared. So we still have the number 24 and the number 16. And we can do the prime factorization for those. But for the number portion, you don't necessarily have to do the prime factorization technique. You can use method number one for just the number portion, like we learned on the other side, okay? If you wanted to do that route. Or you can do everything in prime factorization. So 24 is 2 to the third times 3 times x to the third times y squared. That's what that becomes. This one becomes 2 to the fourth times x squared times y squared. That's what that one becomes. So my GCF, based off of this right here, look in both lists. The big numbers are the base numbers, the little numbers are exponents. And remember, exponents are not numbers, they're exponents. Is there a 2 in both lists? Yes, write a 2 down. Is there a 3 in both lists? No, move on. Is there an x in both? Yes, put an x. Is there a y in both? Yes, put a y. And then put the smallest exponent for each of these bases. On a 2, overall, what's the smallest exponent? Well, this is a 3, that is a 4, so 3 is the exponent. On the x's, this group has an x to the third, this has an x to the second. The smallest exponent is a 2. Go to the y's, this exponent is a 2, this exponent is a 2, so this exponent is a 2. This is the GCF, and the number portion is 8. So 8x squared is the GCF for this expression and this expression, between those two. This GCF technique, okay, or finding the GCF, is the very first step for every factoring problem that you do. You have to see if there's a greatest common factor every single time. Before you do anything else, you look to see if it has one. If it does, you factor it out. Here's how that works in a polynomial setting. Okay? First step, factor out GCF if possible. Not always possible. Well, the GCF in a polynomial setting is basically, this is just reverse distributive property. In the distributive property, if I have an A times a B plus a C, we would distribute the A, and we get A times B plus A times C. Well, in factoring, this A is common to both terms, which means it's your GCF. If it's common, you can bring it out. Bringing it out means, or factoring it out means, to rewrite it back into a parentheses setting. Remember, factoring means to write it as a product. This is a product, A times that quantity. So what we're going to do is the distributive property backwards. We're going to factor it back out. So this followed by this goes like that. You factor that out, okay? So if I give you this example, 15x squared y to the third, 10x cubed y minus 25x squared y to the fourth, and I ask you to factor out the greatest common factor, then we need to identify the greatest common factor. There are three terms. It's like having three of these. See, this was only two. This is three of them. So between the three, we got to find the greatest common factor for 15, 10, and 25. And you can do that using this technique, or you can use it using this technique. Either one is fine with me. For numbers, this to me is usually a lot faster. So I usually resort to this one right here. And most of you guys will like this one, use this one also, because I don't have to go and find the prime factorization. What's the biggest number that goes into 15, into 10, and into 25? And almost everybody can recognize that it's going to be a 5. So I know that there is a 5, so the GCF is going to have a 5 in it. And then I can forget the numbers. There's no bigger one than 5. Then I have all these different letters. Well, then I just do one letter at a time. All three of them have an X to some power. That means X is going to be over here. And what is the smallest exponent that I see on X? I see a 2. That one's 2, that one's 3, that one's 2. 2 is the smallest one. Then I look and see, is there a Y in every term? Y, 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 yes. The smallest exponent is a 3, a 1, a 4, a 1. This would be the GCF. To factor this means to write it as a product. The product will be between the greatest common factor and whatever is left over. We have to undistribute this from these terms. So 5x squared y is on the outside. There will be three things in here. 1, 2, 3. 3 things in here. Do one at a time. You can do it as a division, so this divided by this will be this. Or you can think of it this way. 5 times what is 15? 5 times 3 is 15. X squared times what is x squared? Well, that's all of it, correct? 1. Y times what is y to the third? Well, I need a y squared. If I multiply these two terms together, it should equal that first term right there. If it doesn't, you got it wrong. Plus, now do the next term. Now we're doing this one. Same way. 5 times what is 10? 2. X squared times what gives me x to the third? I need another x. Y times what is y? Y times 1. So we don't do anything here. It's all gone. Do the last term, minus 5 times 5 is 25. X squared times what is x squared? Don't need any more x's. Y times what is y to the fourth? I need a y to the third. Close your parenthesis, and that is factored right there. That is how the greatest common factor works. After you've done the greatest common factor, the next one is factoring techniques are based off of how many terms are present. Okay? Now, we factor out a GCF, that's still there, but now we're considering or focusing on here. How many terms does this have? Well, it has, and this one particularly has 3 terms. Okay? So, first thing you start off with is see how many terms it has. It can have 2 terms, 3 terms, 4 terms, or more than that. Okay? 2 terms, there's certain conditions have to apply. I'm going to show you those in a minute. 3 terms, certain conditions have to apply before we can factor them. And only some 4 terms can be factored. And I'll show you a technique for some of those and you can determine if it works or not. Beyond that, we'll learn how to do later on in a different section when we get to polynomials. Here is the two-term factoring techniques. These are basically special 2 terms polynomials. These will be using formulas that you need to memorize. The first one, the difference of 2 squares. The difference of 2 squares looks like this. So the 2 terms that are left will be something that can be written in this fashion. Something squared minus something squared. The difference of 2 squared numbers. So if the 2 terms can fit into this mold right here, then this is the factoring of that right there. It is A plus B times A minus B. So this factors into something that looks like this. Now, you could have put the minus first and the plus second. That doesn't matter, but the pattern is important. And I'll show you an example of this in just a moment. The other one you want to know how to do is the sum or difference of 2 cubes. And that looks like this. And I'm going to show you as a plus or minus, and I'll explain what that means here in a minute. So it can be a cubed plus b cubed, or it can be a cubed minus b cubed. It's a sum or a difference. It's not both at the same time. It's one or the other. When they write a formula that's very similar in both cases, they'll do this because it differs only by signs, and you'll see what I mean here in a minute. This 2-term factors into something that looks like this. It'll be a plus or minus b, a squared, then it's a minus and then a plus, ab, and then plus b squared. And the way you kind of remember here. So what this does in its formula is this. When you have a plus minus in here and they go like this, the tops all go together and the bottom signs all go together. So if this is a plus, then this will be a plus, this will be a minus, and this will be a plus. If this is a minus, then it goes the bottom ones. And the way you can help you remember the signs that go with this pattern, it's the same sign as what it was out here. It's the opposite sign of what was out here. And the last one is always positive. Soap. Factoring's a dirty business. Remember to use soap. Okay? The same sign, the opposite sign, and always positive. And the pattern is the same for both rules. So how do I do this? Here's an example. So the first thing I do when looking at this, I say, does it have a greatest common factor? Is there some number that's common to 16 and 9? No. Is there an x in both terms? No. Is there a y in both terms? No. There is no GCF here other than 1, then we don't do 1. Okay? So, how many terms does it have? 2. It is either one of these formulas, one of these forms, or you cannot factor it. That's how it works. So, I see a minus, I see squareds, I'm thinking difference of 2 squares. If it's the difference of 2 squares, I should be able to identify the A and the B. What number squared minus what number squared produced that? So it basically just means just take the square root of these things to fill in the box. So the square root of 16 is 4. This is just an x. The square root of 9 is 3. This is just a y. A is that, B is that. So we can now factor this according to that pattern. A goes in the front. The B goes in the back. One's a plus and one's a minus. Again, doesn't matter which one you do is which, plus or minus, it doesn't matter. One's a plus, one's a minus, and that one's done. That is the difference of 2 squares. Two terms, again, there is no common factor. At 2 terms, it's one of these over here or it's nothing. Because I see a cube and a plus, I'm going to see if I can fit it into the sum of 2 cubes. If that is the case, there is something cubed plus something cubed to make it work. 8, hopefully you'll get used to this by now. 8 would be a 2, because 2 times 2 times 2 is 8. And 27 is another common one you'll see a lot, and that one's the 3. Following the formula. I always do the signs last, just so you know. When I do factoring, the signs are the last thing I plug in. So this one has 2 terms, and then it has 3 terms. The positions are that base and that base, so it would be A and B. And then it is whatever A was squared. So what is 3x squared? Well, I have to square the 3, which is 9, and square the x, which is x squared. And then the middle term here is the product of these 2 things. So 3x times 2. 3x times 2 is 6x. And then the last part of this pattern is take the b number, or the last one here, and square that base number. So 2 squared is 4. And so then I just remember SOAP after that. SOAP is the same sign, the opposite sign, and always positive. And I am done. That is 2 terms. Three-term polynomials. Before we do the 3-term polynomials, let's see where they come from. Let's see how they are developed. Okay? So when we factor 3 terms, we're going to get a product like this, where it's 2 terms each. So this is a binomial times a binomial. If you can factor 3 terms after the GCF, it will be usually into a binomial times a binomial. Here's where they come from. So I'm going to take 2 generic binomials. And so if that was my answer, what was the kind of thing that it came from? And so if I multiply and all that kind of stuff in this, so that times that gives me a times c x squared. That times that gives me AD times x. That times that gives me BC times x. And that times that gives me B times D. These two middle terms can come together. They have something in common, don't they? They have an X, right? So I can combine this. Go, die. There's a bug. So ACX squared, this comes out to be AD plus BC, and then the X here. And the last term is BD. So you can see that I have three terms. 1, 2, and 3. So if I'm given something like this, I need to get into that. Well, I have to do what? Where do these numbers up here come from? Well, these two front numbers are factors of whatever the first number is here. So this is telling me I got to find factors of this first number. And then whatever those are, they go in the first slots here with the X. And then the B times D is the back number. So whatever the last number, the constant is, I need to find two numbers that multiply that. It's going to find their factors, and those go in the last slot over here. And I know I have the right numbers if I can do this little product real quick and get this middle number to be the same. So this little thing right here we use to find the correct numbers, the correct factors. Okay? That's what happens. There's a lot of other stuff that's in here. One more thing I want to talk about is this sign on the last end right here. Whether it's a positive or a negative. This sign tells me if I need to add or subtract to get the middle. See right here, it has a plus sign. Okay, because you don't know what A, B, C, or D is. I mean, so if this is a minus in here, this tells me if it's going to be a minus. It tells me if it's going to be a plus. That's what it tells me. Okay, you'll see how it works here when we actually do a couple of examples, which I'm going to do for you. One of them right now. So here's an example. I'll do an easy one for us right now. Let's do y squared minus 11y plus 30. So based off of our thing right here, a times c is this number in front, which is a 1. So 1 is the first coefficient. There's only one way to get a 1. 1 times 1. So that means a is 1 and c is 1. Does everybody see that? This is the back number, 30. So I need to find the factors of 30. 1 and 30, 2 and 15, 3 and 10, 5 and 6. So here you can see I have 4 choices to be in the back. So B and D could be one of these pairs. One of these numbers is going to be a B and its partner is going to be the D. Our job is to find out which one it is. Because by this little thing I just told you, this is a plus, right? What you're going to do, I need to add to get the middle. And you take this combination. That means one of these multiplies to one of those. The other one multiplies to its partner. And then you're going to need to subtract to get the middle. It seems kind of complicated, but it's really kind of simple. So just pick a number over here. I recommend highly that you start at the bottom of your list. Never start at the top unless you have a great big difference in values. Like if this number is extreme, this number is really large and this one's really small, or very, very, very large, then I'd take one of the bigger numbers up top. Always start at the bottom and work your way up. You're going to run into the answer sooner than later, okay? So we know I'm going to take one of these. If I take the bottom, it's going to be 1 times 5, 1 times 5, 1 times 6. So that's AD and BC. That's what I just did. I need to add to get 11. This is a 5. This is a 6. If I add them, I get 11, don't I? So we have found it. These numbers are A and C. These numbers are B and D. I always put the front numbers in first. 1 and 1 with the variable y. Does y times y equal y squared? Yes. Always check to make sure you're doing things properly. Because these are both the same, it doesn't matter too much. So then put a 5 in and a 6 in the back. 5 times 6 is 30. I needed a negative 11, so both of these have to be negative to get a negative 11. Right? So that means both of these have to be negative to get a negative 11. A negative 5 times a negative 6 is a positive 30. Here's how you can check the middle real quick. That times that is a negative 6y. That times that is a negative 5y. Combine those, you get a negative 11y. Okay. My answer is done. That's the factored form. So let's practice some more. Here's another example, a little bit more challenging one. I'll go just a little bit faster for some of these as we move along. Take the factors of 6 and the factors of 1, so that's pretty easy. 1 is done. 1 and 6, 2 and 3 for 6. I don't have much choice. I'm going to start at the bottom. I'm going to work to these over here. I got a 2 times a 1, a 3 times a 1. That's a 2. That's a 3. I need to add to get a positive 5. That means they're both positive, and I have it already. The front numbers were those. The back numbers were those. You can do it however you want. I usually put the bigger number first, but you can do it however you want. It does not matter. This will be 3x. This will be 2x. The 3 multiplies to that number right there, so 3 times 1 goes there. This number multiplies to that number, and that number is a 1, so a 1 goes there. Everything's positive, so everything's positive, and that problem is done. This is the last example for the video for a 3-term. A little bit more challenging now. The front number is 12, so we need factors of 12. We need factors of 15. 1 and 12, 2 and 6, 3 and 4, 1 and 15, 3 and 5. So now I need to find the combination that do all this and that subtract to give me 11. Okay? So since we start at the bottom, let's just go. Take a 3 times 3, so 3 times 3, 4 times 5. Why did I do that? That's what I did first. If it works, great. If it doesn't work, I'll move on to another one. I don't know what the answer is. See, you never do. You just start. This number is a 9. This number is a 20. And I need these two combined by subtraction to get an 11. Can I make that happen? It's either yes or no. Can I subtract these numbers and get 11? Yes. I need a positive 11, so that means the 9 has to be negative, the 20 has to be positive, and I get 11. This tells me then that those are my front numbers and those are my back numbers. Front numbers, 3 and 4. That times that is that, yes. Now, you can't just throw these in here wherever you want. This 4 multiplies to that number. 4 multiplied to the 5, so this number has to be 5. That's how you know where to put it. 3 has to multiply to 3, so this 3 has to multiply to the 3 right here. This times that is 20, and 20 had to be positive, so that one's plus. The 9 had to be negative, so this one's negative. And that factoring is done. The more you practice this, the better you get. The quicker you get, you need to be really fast at factoring returns. You cannot rely on anything else. You got to learn to factor. Last one is for 4 terms. Not all of these factor into 2 binomials. Okay? So, how do I know if one does? There's a lot of ways to do this. They usually call this factoring by grouping, and you can do factoring by grouping, but I found that the box method kind of like works the easiest because you'll know right off the bat if it works or not, okay? Without having to get too far into it. Here's how the box method works. We'll do it by an example here so you can kind of see. Actually, I'll just draw it out. So you just make a 4 compartment box. And it's 4 terms, so this is where the first one goes, this is where the second one goes, this is where the third one goes, this is where the fourth one goes. Okay? And then what you do for each row in this direction, has to be in that direction, factor out the GCF. Don't go in the other direction, go this direction. So if you do that for both of those, this out here will be a factor. Then you do it in this direction. When you get done, this up here will be the other factor. If it has nothing, or there, now the GCF can be 1. So you'll start using a 1 here. Okay? If it's a 1, you put a 1 out there. So if it can happen, if this thing can factor, it will factor in this technique. If it can't factor, then it won't work. You'll see clearly, okay? So here's an example that uses the box method. 2AC minus 2AD plus BC minus BD. So if I wanted to factor that into 2 binomials, make the box. The first term, the second term with sign, minus 2AD, minus 2AD. BC minus BD. We're going to do GCF this way. Note, if terms 1 and or 3 are negative, factor out negative. I don't have that in this case. These are negative, okay, but these are not. If this was negative, I would factor out a negative going this way. If this was negative, I would factor out a negative, okay, but it's not, so I'm not. So what's common between these 2 terms? B is common between those two terms. What is common between these two terms? Well, they both have a 2 and they both have an A. Now let's go this direction. Now, you don't necessarily have to factor out the GCF in this direction, because if you look at this clearly, this is just a small version of the multiplication table you did back in grade school. 2A times what is 2A times C? C? Yes? That times that must be that, doesn't it? Now, if this worked, that times that will be that, does it? If the answer is yes, continue. If the answer is no, this does not factor in the box method. Okay? 2A times what is negative 2A times D? Negative D, correct? That times that should be that. That times that should be that. And it is. So I know I am correct. Then that and that are the two factors. So this factors into 2A plus B, C minus D. And that would be your answer for the box method. So that's how that works. We'll practice outside this video, and we'll call this one done.